What did you look at?
I think plotting the distance time graph.
You've forgotten. You've gone to distance time graph. That is two-dimensional geometry. Distance time graph is two-dimensional geometry. Here we're talking about transformation. You looked at rotation. Didn't you look at rotation? Hello? Oh God, you've forgotten everything.
Yeah, we looked at rotation.
Hey, no, why didn't you? You're taking us to distance time. The distance time is not part of transformation. Okay? Is it part of transformation?
No.
No. That is two-dimensional geometry. So it is more of 2 dimensions, distance time. Now we are going to look at the matrix transformation, or how to use matrices to be able to solve problems involving what? Transformation. Involving transformation. Now in your senior 2, like we said, you use the graph paper to be able to see what happens to an object when it undergoes some of those different transformations. When an object undergoes a translation, what happens exactly? We are going to just go briefly, look at it briefly. When an object undergoes a reflection, what happens? When an object undergoes a rotation, what happens? When an object undergoes an enlargement, what happens? Okay, you're going to help me with that. I hope you have not forgotten everything, because when you forget everything, it's very bad, because we're going to use the same ideas you discussed in senior 2 to be able to solve problems involving transformation, especially when you're using the matrix method. The other side, you are using strictly graph work, which is geometry. But this time you are going to use the matrices of transformation to be able to do what? To be able to arrive at your result. For instance, what do we know about a translation? Let's begin from there. What do we know about a translation? Anua, want to say something? Anua, what do you know about a translation?
When an object is
Yes, we're listening.
When it's transformed, it changes its position.
Your position is changed. What else? What else? Position is changed. What else? What else do you know about the translation? Cynthia? Okay, what you should know about a translation is, 1, you must have a translation vector, okay? A translation vector. Now that translation vector is represented as a column vector, or is represented as a column matrix, okay? Now our translation vector, I'm just reminding us what a translation is. A translation. A translation, you must have what you call a translation vector. And in the translation vector is represented by a column vector, a 2x1 matrix in that order. Okay, isn't that what most of us recall? In that order, it's represented by that. So it means each point on the object moves x units in the x direction and moves y units in the y direction. So if an object is translated, it means that each point on the object moves x units on the x direction and moves y units on the y direction. So how do we define a translation? A translation is a transformation. Transformation where each point on the object moves a given distance in the x direction and a particular distance in the y direction. That is the meaning of a translation. Okay. Now,
Pardon.
I said a translation is a transformation. Okay. Someone is
Yes.
making noise there. Let that person reduce mute. A translation is a transformation, okay, where each point on the object moves a particular distance in the x direction, or a particular unit in the x direction, and a particular unit, okay, in the y direction. Each point on the object moves maybe x units. I'm just saying a particular distance in the x direction and a particular distance in the y direction. That is a translation. Now that you can represent that in form of figures. Okay, I've just used x to represent the x coordinate and y to represent the y coordinate. I can use maybe 2, 5. Okay, so it means that each point will move 2 units in the positive side of the x-axis and 5 units on the positive side of y. You can even have -2, then 5. So it means -2 means that point will move 2 units on the -2 as the negative side, which is the left-hand side, and 5 units upwards. Okay, so that's the meaning of a translation. You also looked at, when you go back to your book, you saw that when an object is transformed, what happens? Okay, the shape doesn't change. The shape of that object, the image that you get, its shape doesn't change. The size also doesn't change when you are dealing with the translation. Okay. And then you see it is more of a slide. Okay, like you have some object here and you slide it to get an image. Okay, it's more of a slide, but that slide means that there is some vector that has affected it. It has moved a particular distance in the x-axis and a particular distance in the y-axis. That's what you looked at when you are looking at a translation. Okay, I don't know if we need to go back to that. You have those things in your books. You need to just go back and check. That's a translation. How about a reflection? What did you see about a reflection? We saw that when you are reflecting something, when you're reflecting an object, you must have what you call a mirror line. A mirror what? A mirror what? Members?
Line.
You need to have a mirror line. And this mirror line, this time, is not the mirror that you use at home. In mathematics, it's not the mirror you use at home. In mathematics, what are these mirror lines? These mirror lines, we have x-axis, or the line y equals to 0. Another mirror line that you can look at there is y-axis, or the line x equals to 0. Another line that you can have there is x minus y equals to 0, or you can have x equals to y. And another mirror line in that case is x plus y equals to 0, or you can have x equals to negative y. So those are the mirror lines we are going to consider, okay? Those are the mirror lines we are going to consider. So when you are doing these things on the geometrical aspect, you need to draw those mirror lines. When you draw those mirror lines, then you can be able to reflect your object and get an image. You get an image immediately. Now, what do you notice about reflection? One thing you need to notice about a reflection is that the distance from the mirror line to the object is the same distance from the mirror line to the what? To its image. The distance from the mirror line to the object is the same distance from the mirror line to its image. You need to know that, okay? Then another thing that you need to know, another property you need to know is that the line joining the object to its image meets or cuts the mirror line at 90 degrees. That is what you need to know. It is perpendicular to the mirror line. Okay, we are going to use that to be able to generate what we call the matrix or the matrices of reflection. We're going to use those properties. What else do we know about a reflection? We need to see that when you reflect an object, what happens to its image? What exactly happens to its image? Okay, you will see that the image is like a flip over. Okay, a flip over. When you look at a mirror, you get a mirror and put it in front of you. What happens? You see that your image is looking at you. Okay, you see, that is what happens exactly when you are dealing with a reflection. Okay, yes. Now, you also looked at what we call you looked at a rotation. What do we need to know about a rotation when you're talking about a rotation? What exactly do we need to notice? Okay? When you look at a rotation, you need to look at, you talk about the center of rotation. It's very important that you bring out that. Center of rotation is very important. Center of rotation. Center of rotation, then you need to also look at the angle of rotation. What is the angle of rotation? So when you're describing a rotation, you look at all these things there, the center of rotation plus the angle of rotation. It's important that you take note of that. So when you're looking at the geometrical aspect, that is what you looked at. You looked at the center of rotation and the angle of rotation. Okay. Later on we shall see, because we are going to use the same aspect, those properties, we shall use them to generate what we call the matrices of what? Of rotation. Then you also looked at enlargement. You looked at enlargement. What do we know about enlargement? I know you've forgotten. I'm just trying to remind you. Okay, when you talk about an enlargement, what happens? What do we need to know? An enlargement, you look at the center of enlargement. Center of enlargement. You need to know it, okay, before you think of enlarging an object. Then you need to know the enlargement scale factor. Enlargement scale factor. What is it? Later on we shall see when the image of the object, when an object is enlarged and its image is smaller, what is the implication in terms of the scale factor? Or when the object and the image lie on the same side, what is the implication? When the object and its image, they lie side by side, the center of enlargement is in the middle, what is the implication there? We shall bring in the negative, the positive, bring in the fractional scale factor. All those things have to be into play if you're looking at an enlargement. So it's very important you go back and revisit that. Okay, the moment you revisit that, life becomes very easy for you when you are dealing with enlargement. So we looked at the geometrical aspect of transformation in senior 2. Please go back and revisit that, because today we're not looking at the geometrical aspect, we're looking at the matrices of transformation. Now, when an object is transformed, you know that what happens to its image. Its image, there's something, okay, that happens to its image. Either the shape changes depending on the nature of the transformation, or the shape doesn't change. The size sometimes changes depending on the nature of the transformation, or it doesn't change. Okay, so all these transformations, they have different effects on a particular object. Okay, can I get some questions? 1, 2, and then we proceed. Anything that needs to be repeated just for clarity? The silence. I don't know why are you very silent. Yes, anything from the students that needs to be clarified upon, and then we proceed.
What does transformation mean?
Transformation.
I entered late.
Hmm? Why did you enter late? Who is asking?
It's Letitia.
Letitia, Letitia, you didn't do transformation in senior 2? The graphical method.
I just don't remember the term.
But you did.
I think I did.
Okay, let me not go far away. For you, if someone said you are transformed, what does it mean? That you have been transformed. What does it mean?
You have been changed.
Good. That is it. Okay. You have been changed. Okay. It means your behavior has changed. Okay. Your behavior,
Yes.
your moral aspect of life, your morals have changed. You liked, I don't know, doing what, there's certain particular things you used to do them, and now you cannot do them. Okay. But your shape has not changed. You have remained, Letitia, the way you are. Or sometimes we can say that you have put on weight. Are you getting the point?
Yes.
Due to what? Eating good food, balanced diet. Are you getting the point?
Yes.
For instance, when you come back to school, say, hey, you have put on weight, you have grown. It means you have been transformed. Are you getting the point?
Yes.
Your size has increased. You are, I don't know. You can name all those things. Okay. That's the meaning of transformation. Now, if you are to bring that same knowledge to mathematics here, we look at objects. Sometimes when these objects undergo particular changes, what happens to their image? Some of them do not cause any effect on the images. Some of them cause effects. Okay. In terms of change in size, in terms of the shape changes. Okay. Are you getting the point? Letitia, are you getting it clearly?
Yes.
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 So now you need to go back and revisit. You need to go back and revisit. That's why it's very important. You need to know the geometry aspect of transformations. Because the moment you know it, then it is going to be very easy for you to do what? To understand these matrices of transformation. But if you still don't know what effect a translation causes on an object, what effect a reflection causes on an object, what effect an enlargement causes, what effect a rotation causes, then you are going to be left behind. Okay, you need to go back and revisit. We have no time. I have been hearing rumors that you are doing exams in May. I don't know how true it is, but let's assume it is true. Let's assume what? Letitia? Letitia? Let's assume let's assume it is true. What would you be doing? You need to go back and revisit before the day ends. Are you getting me, Letitia?
Yeah.
Good. So I want all you students, you go back and revisit whatever you did in senior 2 about geometry of transformation. So the next time you're discussing, life becomes very easy. But now, if you are doing things and it seems to be all new to you, it means there's a very big problem. Okay, let us go back and revisit the geometry aspect. When an object undergoes a translation, what happens? What properties do I look out? When an object undergoes a reflection, what happens? What properties do I look out? When an object undergoes a rotation, what properties do I look out? Okay, it's very important. And enlargement, these are things that we see every day. Okay, for instance, there are particular things we can't see with our own eyes. They have to be enlarged. Like, can you see very tiny particles? I mean, germs and so on. You can't see them. Okay, so you have to use maybe a microscope and so on. That is enlargement, so that you can be able to see. Okay, you know the things here. For instance, a reflection, you may think, why are we studying reflection? Just look at your legs and look at your shoes you're putting on. That is application of reflection. Okay, one shoe is reflected. If you see clearly, one of your shoes is a reflection of the other. That is the application of reflection. So some of the things we may be studying it in mathematics here, but in real life, they are they are applied clearly. Okay, and many others you can look at. So just for the sake of doing something today, because we shall not dwell on only one thing over and over again, majority of us have forgotten, but we are going to try as much as possible to remind us of what these things mean and how can we use matrices to be able to solve problems involving what? Involving transformations. Okay, so a transformation is like an effect on an object. Okay, and there are different types of effects, or there are different types of transformations. We have a translation, we have a reflection, we have a rotation, and we have an enlargement. So each of those ones, they have different effects on a particular object. Someone has something to say before we go to generating the matrices of transformation of the different types of transformations? Yes? Yes. That's so quiet. Doreen or Rishaba?
Yes, teacher.
What do you have to say?
I have nothing to say.
You're just listening.
Yes.
Okay. I've said we have already looked at a translation. A translation, you need to have a translation vector, and it is described by XY, by a column vector in that order, XY. So this should be able to help us to do what? To solve a problem involving transformations. Okay, so I've said the different, I'm going to repeat, the different types of transformations are translation, reflection, rotation, and then enlargement. So because you looked at the geometrical aspect of transformations, we are now going to look at how to generate what? How to generate matrices of transformation, or the different types of transformation. Okay. We're going to look at how to generate matrices. We are starting with the reflection. Reflection. Translation, we already looked at it. A reflection. Now, for a reflection, we want to generate the different matrices of reflection in one, the line y = 0, or the x-axis. We're also going to look at how to generate the matrices or matrix of reflection in the line x equals 0, which is the same as y-axis. We're also going to look at how to generate a matrix of reflection in the line x equals to y, which is the same as x minus y equals to 0. And lastly, we're going to see how to generate a matrix of reflection in the line x equals negative y, which is the same as x plus y equals to 0. Now, these are mirror lines, like I said, these are mirror lines, okay? So always when you're describing, you need to talk about the mirror line. The mirror line, describing reflection, talk about the mirror line. So we are now going to look, for instance, a reflection in the line, reflection in the line, y equals to 0. Okay, you see, or x axis. Okay, that is it. Now, that is it. Now, we are going to use what we call using ij. And I, the point I is, the coordinate of I is 1, 0, and j is 0, 1. We're going to use those two to be able to generate the what? Matrices of reflection. So I'm going to draw something like this, should be able to help us. If it's not clear, please you let me know. That is it. So I represents x, j represents y. I represents x, j represents y. So we have our 0 there. This is I. This is I. The line is x axis. Or you can call it y equals to 0. So we have this 1, 0, and then we have here 0, 1. This is j, and this is I. Okay, that is it, and this is j. Now, what do we need to know about? What do we know about a reflection? What you know about a reflection? If this is our mirror line, members. That's why I said you needed to go back and know this. This is our mirror line. Any point on the mirror line is invariant. What's the meaning of that? Any point on the mirror line is an image of itself. That's the meaning of invariant. When you get a mirror and place your hand directly on that mirror, what happens? What do you see? You're going to see that the image of your hand is also on the what? On the mirror. So that is the meaning of invariant. It doesn't change. It's an image of itself. So we start by reflecting this point here. The point, what's the coordinate of that point? The coordinate is 1, 0. When I reflect it on this line here, because this is my mirror line is x-axis or y equals to 0. This is my mirror line, members. It's my mirror line. So a point I, like this, if you are reflected along this mirror line here, we see that its image also lies along that. So if I reflect, let's say, a point I, and its image, sorry, its object is represented by 1, 0. I reflect it, undergoes what we call a reflection along the x-axis. Its image is given by 1, 0. Why its image 1, 0 is because the point lies on the mirror line. So this point is invariant, is the image of itself. Doesn't change. Now, always, by the way, when you're reflecting, you begin with any point on the x-axis. Then you move to points on the y-axis. Now, we're going to reflect this point here. Remember, our mirror line is this. It's a mirror line. I'm reflecting. What else what do we not know about a reflection? What you need to know about a reflection is the line joining the object. Sorry, yes. The distance from the mirror line to the object is the same distance from the mirror line to the image. Then 2, what do I need to know about a reflection? The line joining the object to its image casts the mirror line at 90 degrees. So if you are to construct, you're supposed to construct members, you're supposed to construct, okay? You are supposed to construct, but for now, I'll not construct, I'll just put a 90 there. I'm supposed to construct a perpendicular here, put your compass here, make an arc here, put your compass, make an arc here, and then put your compass here, an arc here, then here, then join. So you see that it makes an angle of 90 degrees with the mirror line. Now, we said that the distance from the mirror line to the object is the same distance from the mirror line to its image. So if this distance are 2 units, 10 small squares, this is also 2 units, 10 small squares. Okay, so the image of this is right here. This is J complement. That's the image. What is the coordinate of this point here? You are going to see clearly that if this is J, the image of this point here is 0, 1, undergoes a reflection along the x-axis to give us J complements. This point here is given by 0, negative 1. So in other words, if I'm to combine now, sorry, you're not seeing that. If I'm to combine the two, it means I have I, J. This one is 1, 0, which is here. I'm writing it here. This one is 0, 1. Undergoes a reflection through the line y equals 0 or x-axis to give us the image, which is I prime, J prime. The image of this is 1, 0. Why? Because why is it the same? Because we said it is invariant. And the image of this, when it undergoes a reflection, it gives us 0, negative 1. So that is the matrix of reflection in the line y equals 0 or x-axis. Is it okay, members? Is it okay?
Yes.
Have people understood something there? So this is what we are going to use. Let's avoid cramming. Some of us, we prefer to cram. Cramming is not good. You cram that, you're going to fail properly, because if you forget, you're finished. So this is how we generate. So next time they ask you, when they say